Those were useless.
What do you mean?
Like the different atomic models. Like
Well, that was looking at the history of how we got to where we got and how we figured out those things. I don't think that was useless. What I said about the octet rule, it still works some of the time. You just gotta know when it doesn't. We'll talk about that. But it's still, it's not like I completely throw it out of them.
okay.
Yeah. Okay? So, if you remember John Dalton was the guy that was the English school teacher that I thought taught English and was really good at science, and really he was just from England. You guys like poison ivy. So yeah, he was the guy who he did a whole bunch of stuff. Came up with the law of definite composition, or at least a big part of that. He did a lot of stuff with gases. He came up with the law, his own law, of how when you've got multiple gases in a particular system, how they relate to each other from a pressure standpoint, which is really interesting. What essentially he noticed is that gases, if you got multiple gases in like let's just say we've got some sort of container that we got multiple gases in it. What he found out was that each gas exerts pressure independent of each other. What I mean by that is if I have like that, and I've got hydrogen gas in there, I got oxygen gas in there, I got nitrogen gas in there. Let's say the nitrogen gas exerts 1.4 atmospheres, the oxygen gas exerts 0.7 atmospheres, and the hydrogen gas exerts 0.5 atmospheres. What I notice is that these individual gases exert pressures that aren't dependent upon each other. So what I mean by that is if I took the nitrogen gas out, the other two gas pressures would stay the same. Okay?
Why? Wouldn't it have more space to move without nitrogen gas?
Yeah, but they're still going to collide with the wall at the same amount. Still going to exert the exact same pressure. Okay? So what he essentially studied is if I can figure out the individual partial pressures of each of these guys independently of each other, and then add them all together to get the total pressure of the entire system. Okay? So when we talk about partial pressure, I'm talking about specifically the pressure of one kind of gas. Okay? So when I talk about total pressure, that would be all of it. So that P1 I could have said PO2, P2 could have been PN2, P3 could have been PH2. Make sense so far? Questions? Alright, I had a whole bunch of stuff that I was going to derive, but I feel like in the past I haven't gotten to the last problem. I've had as much time on the last problem as I would like to have, so I'm going to leave the derivation to your reading in the book of how the math came about. Here's what I mean. I'll just briefly state it. This equation is derived from the ideal gas law. You're probably like, how does that work? Well, you'll see it when you read. I'm not going to say if, when you read. I'm telling you, this book is very helpful read. I've been saying that for a while. If you read any book in high school, that'll be the most helpful. What'd you say? You get adopted, you don't? Alright. Here we go. We got a particular situation. A mixture of helium and oxygen can be used in scuba diving tanks to help prevent the bends.
Isn't nitrogen leaving the blood? So the pressure outside?
That sounds, I have no idea, but that sounds like a logical thing. You probably would know it. You seem to know a lot of random facts.
That's right too. I'm a lot
I know that there's an issue that when you get too deep, there's there's pressure effects that are.
It makes more nitrogen gases all over the blood.
Yeah.
And then when you come out, it leaves the blood, but then it's has air bubbles in your bloodstream, which when they hit your heart, it can cause muscle damage in the muscles, or from the major arteries. It can kill you.
Yeah.
It can kill you.
Interesting.
Or cause severe brain damage too.
That would make sense.
Yeah.
You won't want floating bubbles running around your brain. Doesn't sound like that'd be a very good thing to have.
The bends kill you.
The bends. Okay. Anyways, I kind of want to look that up now. That sounds kind of quite interesting.
Yeah.
So don't go scuba diving too though.
Or come up slowly. So it dissolves out of your blood slowly.
Oh really?
Yeah.
Well,
That's why
that's all.
That's why you don't like swim as fast as you can to the surface. That's why they have you wait below water and then kind of get higher and higher.
How do you know these things?
I don't remember. Was it middle school science?
I
guess you weren't here.
I don't know. I don't remember.
I don't know. I looked this up a couple times.
All right. Anyways, so particular dive tells you what you got. You got a certain amount of helium, and those are the conditions. And then you've also got there it is, oxygen gas. Under the other conditions, they're pumped into a tank with a volume of 5 liters. Calculate the partial pressure of each gas and then the total pressure under the new conditions. So, how do you think we should do this? Just be very quiet and wait for Mr. to do it. That's how we should do it. Okay. Alright, so essentially what we have here. Okay? We got volume, temperature, pressure for one condition. Volume, temperature, and pressure for another condition. And notice these are before they get pumped into a new tank. So what don't we have in these conditions? Moles. That's a pretty important thing. I want to know how many particles I'm pumping into that new tank. Does that make sense? Because when I pump it into that new tank, under different volume and a different temperature, I've got to be able to know how many particles I pumped in there. That make sense? Okay? So the first thing we should do is identify how many moles of my my gas I have. So it was helium and oxygen gas. So PV equals nRT. Okay. Where's P? 1? V? And what is that in Kelvin? 298? Sound right? Yeah? Issue, I know.
I looked it up. It's not nitrogen, it's just various gases.
Are they really comfortable?
That's what they have like decompression tanks. You're going in a submarine. That's what that's for.
Makes sense.
I don't know where I
Where do you learn most of the things? Reading, probably.
He remembers what he
Reading.
reads.
He remembers what he reads? I don't remember what I say, so I can't remember what I read.
I don't remember what I say. I remember what I read though.
I can't remember what I read, can't remember what I do. What we get?
Tell me some book about like undersea stuff.
Helium, how many moles? Hydrogen, how many moles? Probably less. Helium, not helium, or hydrogen. Alright. Now we got new conditions, and it says calculate the partial pressure. Well, what would we be doing here then? Let's say that again. I think you're right.
You take them all, each one of those, and put them into new conditions to find partial pressure.
Yep. So I want to find the pressure of helium, the partial pressure of helium, and I want to find the partial pressure of oxygen gas, because I know if I can find their two partial pressures, they act independently of each other. If I can find their two partial pressures, I can find the total pressure by doing what? Adding them. I'm guessing the pressure is going to go up significantly because I'm taking these two, putting them into a much smaller volume. Partial pressure of helium is
9.3.
and of your oxygen gas, a little less.
2.4.
So we found the partial pressures. I would answer this question by saying my partial pressure of helium is 9.3, my partial pressure of oxygen gas is 2.4, and the total pressure of my new tank after I took the two and put them together would be what?
11.7.
Yes. Okay?
That's pretty high pressure. 7.7 ATM, that's a lot.
It is. Questions on that? So we had two gases in their separate containers. They were pumped into a different container with a different volume. To figure out how many particles we had in each original container so that we could figure out the pressure they would exert in the new container. And then use Dalton's law to figure out the total pressure. Okay? But here's something that's really, really important. It's called the mole ratio. Try thinking, well, why is that so important? Okay, well, you'll find out. You can also, I don't have time to derive this, but you can also do mole ratio this way. So I would add that in somewhere. All those things equal each other. So I could remove this and say that the number of moles is going to be proportional to your pressure, like that. Okay, and it had to do with what really Dalton figured out. He figured out that really your pressure is the number one result is going to be based upon how many particles you have. The more More particles, more pressure. Okay? You're going to use that more than you probably think. So let's use it a couple times. Told you everything in advanced chemistry was ratios, so do it. So mole fraction is just simply a ratio or a proportion. Okay? Partial pressure of oxygen gas observed. 156 torr in air with a total atmospheric pressure of 743. Calculate the mole fraction of oxygen gas. Well, we didn't get moles, but we did get what? Okay, and we know your P1, or the one you want, and your P total. That doesn't seem too hard, is it?
That was it.
Yeah.
Oh, okay. Sweet.
So it is.
So 21%.
Yeah, essentially 21% of it, of the amount of, because remember we said that a certain volume of particles has a constant number of moles worth of stuff in it. So if I got 4 liters of 2 different things, I get the same number of gas particles of those 2 different things, right? So if I can figure out how much pressure they exert, I can figure out really the percentage of the gas. So 21%, and that makes sense if you think about atmosphere is really how much oxygen percentage. You guys remember?
Oh,
It's about what? Yeah, it's I think a little closer to 21%. I think. Nitrogen's like 78. So it's like 21 oxygen, 78 nitrogen, like 1%, a whole bunch of other gases.
So there's a
No unit, yep. It's a ratio, or a proportion, or a, however you want to call it. Okay, unitless number, that gets used for something later, you'll find that out when we get there, when we get to Raoult's law. Raoult, that's a new one you all have not heard of. Okay, why don't you guys do this one, I don't think this one's any more difficult.
In this chapter?
Yep. I think it's tomorrow. Maybe Monday. Does that work, someone? You don't mind that noise, but not the squeaky shoe? Can you fix squeaky shoe? Little WD-40.
Hey, anything rubbing on the concrete is like really hard.
Like a rock.
Yeah.
Alright, so you're done? What's the partial pressure of our nitrogen gas? Not partial, yeah, partial pressure.
Already gave us that.
Of nitrogen gas?
No, I'm sorry, I never read it. No.
593, they gave you the total pressure,
That's what I
right?
meant, yeah.
Okay? Alright, let's turn to page 204. This is the stuff you remember from regular chemistry, you guys hated it.
204?
204. We will talk more about the theoretical concept that is vapor pressure.
Yeah, you're right. I missed it.
Do you remember when we did the trapping the gas over water type of thing? It was one day and you guys really didn't like it. We're going to do that here. So if you look, the top of 204 is one of the ways that they figure out volume of a gas that they are producing from a reaction. So if you look at that visual, please be on this page so you're following along so that, because I want you to understand the concept here, because I don't think the concept's overly difficult. if you can understand what's happening, I think the math becomes easier. Okay, so as you can tell, there's something in that test tube, right? Okay, they're heating up whatever is in that test tube, a reaction is occurring. The reaction is producing a gas. That gas is going into the test tube, or into the little connection pipe, and up and into the inverted reservoir of water, which was completely full with water at one point, and the gas did what?
Displace the water.
It displaced it. It displaces the water until the pressure in there becomes equal with what pressure? Think of a barometer.
Oh, the atmosphere pressure.
Right, the atmospheric pressure is going to be what's holding the reservoir where it is, and so it's going to push out the water until the pressure on the inside is equal to the pressure on the outside. Okay? Now, here's where a lot of times gets messed up is, yes, let's say it looks like oxygen gas is the one that got produced. Okay, it goes up, oxygen gas goes through the water and goes into the opening, or creates the opening. That is not the only gas there because of a really pesky thing known as vapor pressure. Any of you remember anything about vapor pressure?
It's the water molecules that escape liquid state in the gaseous form.
Okay, you guys know that evaporation can happen at any temperature, right?
Yeah.
Okay, the higher the temperature, the more water particles will evaporate. Okay, well, it's kind of like a theoretical evaporation, which is it's really goofy. I like to kind of just say that what happens here, like say this is the surface of the water, this is let's say that's at 25 degrees Celsius. There's a certain amount of evaporation that occurs. And in our heads, and even in my head, I think this evaporation is just going to go up into the atmosphere, right? Well, not quite. Because the atmosphere is exerting a pressure down on this water, not allowing anything to really release. So how I a lot of times view this, I know it's not completely correct, but it helps kind of understand what's going on, is there's a theoretical bubble here. That when you have a certain temperature, some of this water starts to evaporate, starts to exert a pressure upward. Okay? Not enough to be strong enough to overcome the pressure of the atmosphere downward. And if you remember, when the vapor pressure equals the atmospheric pressure, do you guys remember what happens? What you could call equilibrium, but there's a very important process that happens. It starts with a B, ends with oiling. You guys remember that? Okay. So what happens is as soon as you can get the vapor pressure with enough pressure to equal or overcome the pressure pushing down, it allows it to be able to displace the water and bubble and get out, essentially. So when we talk about vapor pressure, it's kind of like a theoretical bubble. Okay? However, when you've got an inverted beaker, whatever you would call that thing, okay, there's no gas in there initially when it's full of water, right? Okay? Then you're displacing it with oxygen gas in this context. Okay? Well, there isn't the only pressure that's existent here is the pressure pushing down on the reservoir water there. And so you actually do get some water vapor particles that do evaporate and do mix with that oxygen gas in this context. So, is it correct to say all of that gas in that inverted cylinder is oxygen gas? No. Some of it is what? The vapor pressure that is from the H2O. Okay, and I could pull out my, 51st edition of my chemistry and physics handbook over there, and I could show you what the vapor pressure is at every particular temperature. I think I'm assuming it's somewhere in here. It's not, is it? Darn it. Okay, it might be in the back of your book somewhere. Regardless, they'll have to tell you then what the partial pressure is of oxygen gas, or not oxygen gas, water vapor for you to be able to solve this. Because there's a certain amount of vapor pressure due to the water at 25 degrees. As it goes up, the temperature goes up, so does the vapor pressure. As the temperature goes down, so does the vapor pressure. So if you look at the problem we're about to do, okay, it tells us the vapor pressure of water at this temperature is that. Unless there's you might be able to find a table in your book. I can't remember off the top of my head if it's there, if there's a table here. I remember there was in your regular chemistry book. We looked at it. Okay. Otherwise, you can grab your 51st edition of the Chemistry and Physics Handbook, that you got sitting at in your own library at home.
How do they
Just pull that out.
How do they find this?
Great question. I don't know. Well, that's okay. I wish I did, but I don't. Okay. So here we go. We got a solid potassium chloride. Looks like it's the same situation. I think that's what's in the picture, isn't it? KClO3. Yeah. Okay. All right. So imagine what's happening here. You're reacting that. Oxygen gas is getting produced. It's going into the reservoir, but it's not the only gas that's getting into that volume. You've got some of the water vapor that is also going in there. Okay, let's read what we got here. We got oxygen gas collected by the displacement of water at 22 degrees. So let's say that our temperature, and we'll say it's our total temperature, our final temperature, however you want to look at that. It's 295 degrees, not degrees, just Kelvin. We've got a total pressure of 754 torr, and that would essentially be what the atmospheric pressure is. Does that make sense? We know typically atmospheric pressure is 760. It's telling us it's a little lower than what it normally would be. Because remember, that's what's holding, when it reaches equilibrium, that's what's holding the volume inside the cylinder there. Okay? The volume of the gas collected is 0.650. Calculate the partial pressure of O2. And the mass of this. Oh yeah. Sweet. So it's really twofold. Partial pressure of O2 is really easy. In this context. Pressure of O2 plus pressure of H2O. Do we know the total and the H2O pressure? Could we find the oxygen pressure in that? We have total pressure of 754 torr equal to plus what, 21 torr? So our partial pressure of our oxygen gas there, it's going to be most of it. Subtract, get what, 733? Okay, that's pretty easy. Let's try to think how we're going to figure out the mass of my thing burned.
We can find the moles of oxygen.
And then stoichiometry back.
Yeah.
Everybody see that? I've got enough conditions. Now that I know the pressure of my O2, along with my conditions here, I can use the ideal gas law to find moles of O2. Then I've got a balanced chemical equation, and I can go backwards to figure out the mass of my KClO3. So, moles of O2 would be my pressure, which it has to be my partial pressure of O2, not total pressure. Does that make sense? So, 733.
Yeah.
You need to make it ATM.
Oh yeah, oh yeah. Woo, good call. 0.964 approximately. Volume, do we got that in the right unit? Yep. whole number is gonna be a small number. 2.59 times 10 to the negative second. And then we would finish by doing stoichiometry. And since we're already at moles, it's a two-step process, not a three-step process, right? Okay, I want to get over the bridge so I can get to moles of my KCl03. The ratio looks to be a 2. Okay. And then I'll give you the molar mass of this guy, 122.6 approximately. .12 is your answer. A little bit of work, but still stuff that we know, right? We know how to do ideal gas law, we know how to do stoichiometry. Now we're just looking at a real life situation where we can't assume that the whole volume and the whole pressure in that particular chamber of gas is just oxygen gas. Anytime you're collecting it in some sort of trapped container, you're going to have water vapor in there because of the evaporation. Thankfully, it's a constant. Like, it's dependent upon the temperature. So if you know the temperature, you can just look it up in a book and figure out what the vapor pressure is. It will be that every single time. Okay? Yeah, if they don't ever give it to you, just get your handbook of physics and chemistry at home and just pull it out and look up vapor pressure. Let's see if I can find it in here.
It looks pretty old for me, 51st.
It's like 1970 and 1971.
So I'm guessing